Good. Welcome everyone to this presentation on multiscale scene localization for remote sensing imageries with a focus on detecting damage to critical infrastructure. This work was carried out by myself, Yuri Pushkarenko, it's me, and Professor Volodymyr Zaslavsky from the Taras Shevchenko National University of Kyiv. Okay, today's presentation will cover some motivation for this research, state-of-the-art methods, and the objective of our work. We will dive into the main results we got, explaining how we overcome specific challenges during this particular research, and we will finish with a real-world case study in Ukraine and our conclusions. So, as you can see, with the exponential growth of remote sensing data, current methods face challenges in efficiently processing and analyzing such large data sets. Convolutional neural networks like CNNs are limited due to their small receptive field, making them inadequate for large-scale damage assessment. Vision transformers, it's a good solution, but while more powerful, are computationally expensive and less efficient for large data sets and near real-time making decisions. So this makes damage detection in critical infrastructures like bridges and energy grids a really complex problem. So you can see that for today we have a lot of different sources of satellite imageries and remote sensing imageries. So it's satellites, it's UAV, balloons, airplanes, and so on. Also, we can see that we have a current method limitations, and of course you can see the some example of satellite imageries with some specific localizations for some specific bridges, airports, power energy grids, and so on. So let's go further. Okay, our objective is to develop a scalable and accurate framework that can balance both global and local damage detection. Traditional methods struggle with this dual requirement, and our solution integrates the strengths of CNNs and vision transformers, optimizing them for a specific task of detecting large-scale damage, while still capturing fine details like cracks, some damages, some small damages, big damages, and so on. The main challenge we face is a limited receptive field in traditional convolutional neural networks, which makes it difficult to capture the full global context of a large infrastructures. This often leads to missed localized damage, such as small cracks, when analyzing large structures. And our research aims to address this issue by expanding the receptive field. But you can see that on the image we have different strategies, not we, but the current situation in computer vision communities. The different strategies for analyzing such problems and imageries. So for A, we have a predict from multiple image scales with a single filter size. So as you can see, it's quite not scalable and problematic because it takes a really huge number of computational times. And we of course we can do predict from a single feature map with a multiple filter size. You can see it, and that's a problem because we can control the attention between a different context. For example, we cannot do the localization, for example, for ships and for power energy grids, and that's a problem because it's a two different context. So this is a challenge. Also, we can predict from topmost feature map with a single filter size. Of course, that's less computational expensive, but the same situation as a B problem, that we have some problems with localizing some context, and predict from multiple feature maps with a multiple filter size. Yeah, we have a context, but we don't have a computational effective thing. So how we can address these problems? First of all, to overcome this limitation, we combine a global convolutional network, which is already defined in some most popular paper. It's a large kernel methods improve semantic segmentation by global convolutional network, which captures broader global features. And with a swing transformer, which refines local details using attention mechanisms. And some interesting thing, the SC module, it's like a special cross-scale convolution model. I'm sorry. Ensures that both global and local features are balanced, providing an effective solution to the receptive field problem. Okay, let's go further. Our proposed framework consists of three key components. First, the GCN, it's a global convolution network, is responsible for extracting global features at a regional scale. Next, the swing transformer focuses on refining those details using attention mechanism, allowing us to some kind of on a machine state to zoom in on critical damage. Finally, the SC module combines and balances features from multiple scales, ensuring precise damage localization across all levels. So you can see the network on the screen, and to build and test our model, we used a high-resolution image from multiple sources, included datasets from Maxar technologies and crowdsourced imageries. The data is processed through the GSM for global scene analysis, then the swing transformer zoom in for local damage identification, and finally the SCSC integrates all features for accurate damage localization. So not so big deal. The GCN is a critical in expanding the receptive field. So we should think about that as a global context. So we don't think about it like some small things on imageries. By using large convolutional kernels, the network can capture the full context of the scene, which is essential when assessing large-scale damage like the collapse of an entire bridge. And mathematically, this is represented by convolving the input image X with a large kernel W, producing an output feature map X prime. This process allows the network to extract broad regional features efficiently. The swing transformer in their way plays a key role in focusing, as I said before, some kind of zooming on specific areas of interest, such as cracks or structural damage. So you can see Irpin Bridge near Kiev. It uses non-overlapping windows and attention mechanism to efficiently detect local damage within a large-scale scenes. This method ensures that even the smallest details are not missed, especially when combined with a global context from the GCN. So you can see a really standard formula where we can describe the work of attention mechanism. So you can see an attention with a 3 vectors: query, key, and value, and softmax function. So let's go further. Actually, the SC module balances global and local features to ensure accurate damage detection across multiple scales. By combining features from both the GCN and SWIN, the SC prevents the loss of important details or global context, ensuring that both large and small damage areas are captured. This mathematical operation sums features from different scales, weighting them appropriately to balance global and local context. So here is how the receptive field expansion happens mathematically. You can see it. And first, the GCN uses large kernels, as I said before, to capture global context by convolving the entire scene, which expands the receptive field significantly compared to traditional CNNs. Next, the SWIN transformer applies attention mechanism, focusing on important details within a local window. So we should understand it. Our framework, let's go through our results, like quantitative performance results. Our framework outperformed traditional CNNs, CNN-based methods across several key metrics, including precision, recall, and standard intersection over union. For example, our proposed model achieved an intersection over union 88.3%, significantly higher than the traditional CNN model, which had an intersection over union of 84.05%. These results demonstrate the effectiveness of our approach in capturing damage at both global and local scales. Also, we tested our model against several well-established methods, including UNet, SIGNet, and vision transformers across 2 datasets, XBD and crowdsourced aerial imageries. In all cases, our model outperformed the alternatives with a higher precision recall, F1 score, and intersection over union. These highlight the robustness of our framework in different scenarios and across different data sets. This visual example shows how our model effectively detects damage at both global and local levels. And scene 1, we focus on specific cracks detected within a larger structure. And scene 2, we see the broader analysis of a full breach with localized damage areas clearly marked. The combination of GCN and SWIN allows for this dual focus. So it's actually it's a Mariupol city, so near epicenter. And another one, in a real-world case study, our framework was applied to assess damage to critical infrastructure in Ukraine, including bridges and power plants and special buildings. When I say special buildings, I mean some buildings that related or either critical infrastructure, either military units. The model detected 95% of the damage across 300 plus buildings, significantly outperforming traditional CNN methods. This application highlights the framework's potential for faster, more accurate damage assessment in conflict zones. So it's because we know that conflict zones, it's a big deal because we have no any access to conflict zones. I mean, civil engineering people or rescue teams. So we need to some kind of identify it more faster in more faster way and to understand what's going on there. And in conclusion, our model successfully solves the receptive field problem, allowing for both global and local damage detection in a single model. It outperforms traditional methods, particularly in large-scale damage scenarios. Future work will primarily focus, I suppose, on optimizing the model for SAR data and applying the framework to natural disaster damage detection, because it's also that's like another problem that we should solve, as well as providing a visual geo search. So when we, for example, when we found some cracks or issues or damages and some bridges, we should provide some understanding where the problem is. So with this particular thing, we should identify and geocode this object or this feature to some real coordinates, I mean geo coordinates, and to get some information about the area of interest. So that's it from my side. Thank you, everyone, and maybe I'm happy to take any questions.